Hi, in this video we'll talk about the theoretical big O of merge sort. So we have seen that merge sort is pretty fast. Now exactly how fast is it? Is it still polynomial but with a smaller power, or is it something else? Well, I think we said at the beginning it's n log n. So how is that the case? Now, if we look at the pseudocode for merge sort, one of the this is a recursive call, but then one of the operation, the most important operation, is the merge. So let's think about what's the time complexity of merge first. So the merge, we've seen how it works. It's basically just iterate through both of the sublists, and it goes through each of them once, right? And how big are the sublists? Well, the sublists are together, they add up to the original list of size n, right? So basically, it should be fairly obvious that merge is the time complexity is simply O of n, or linear. And here is the pseudocode again. Now, because the merge sort has two recursive calls, so it's probably not immediately obvious what is the time complexity is. So let's just write out the time complexity recursively as the pseudocode itself. So the t of the time of merge sort given as input size of n, that is the time it takes to sort the first half of it. That's why n divided by 2, right? And then plus the t, the time it takes to sort the second half, and then plus the time it takes to do the merge, which we already established, and that is n. So this is basically, yeah, t of n equals to 2 times t of n divided by 2 plus n. So let's take a look at how we can further kind of simplify this expression so that it becomes an expression, a function of n. So the first thing we can do is we can further expand t of n divided by 2 using the definition of t of n. So that is nothing more than simply, replacing n here with n divided by 2. And if we expand this part, then we actually get 2 times t n over 4 now, because n is now n divided by 2, so that becomes n divided by 4, and n again will replace n with n divided by 2, so n divided by 2, and we keep the original terms. And if we kind of multiply things into parentheses out and do a little bit of simple math and all that, we ended up with 4t of n divided by 4 plus 2n. Okay, and we can do this again. We can substitute n divided by 4 into n here, and then we're going to end up with this expression, and then we're going to end up with 8t n divided by 8 plus 3. And then hopefully you kind of see the pattern here already, 4t n divided by 4 plus 2. The next one is 8t of n divided by 8 plus 3. And then the next one would be 16 times t n divided by 16 plus 4, right? So, and when you look at this carefully, that this number here is, well, actually this number here is the 2 to the power of this number. So if we replace 4 or 3 or 2 or 1 with, say, a variable p, then we can express this number, 16842, as 2 to the power of p, right? And so we can keep going like this. And when does this end? Well, we know it ends with t, when the size of the input is 1, right? T of 1. So that's remember that's the base or terminating case in the merge sort. So now we have these two expressions, and that is the terminating case. Then we can try to solve for or express p in terms of n. And how does that work? Well, we basically um, because this expression can be converted to this expression, that basically means n divided by 2 to the power of p is going to be equal to 1, and that gives us two pieces of information, because it tells us that n can be expressed as 2 to the power of p, or p is log of n. And if you do a little bit of substitution, if we p, right, we say p is log of n, so this term becomes log n times n, or same as n times log n. And now when you put p, when you substitute p with log of n, this expression becomes 2 to the power of log of n, which basically is just n itself. And that's how we end up with this expression. And now the only thing that is a little out of place here now is t of 1, and that is the terminating or the base case for the recursion. And it really doesn't matter what it is, but the important thing is we know that it's constant, right? A base case is always constant time operation. So we can denote that with a c as in a constant. And this is what we have for the time it takes to merge sort input of size n. And if we look at this expression here, we know pretty much that the dominating term, well, first of all, we can get rid of c because it's a constant, and as we said time again, big O doesn't care about a constant. So this expression becomes n plus n times log of n, and this is the dominating term. So we just, in terms of the big O, what we have left is just n times log of n, which is the time complexity of merge sort.